Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
1835 Siméon Denis Poisson Mathematical Theory of Heat. The esteemed mathematician Siméon Denis Poisson's Mathematical Theory of Heat, published in 1835, represents a cornerstone of 19th century physics, attempting to establish a rigorous mathematical framework for understanding heat phenomena. This essay endeavors to provide a thorough, section-by-section critical evaluation of Poisson's work, scrutinizing its core claims, methodological approaches, and internal consistency. Our assessment will primarily focus on the work and its original content, with external context employed primarily when crucial for illuminating the validity or interpretation of its central arguments. We commence by analyzing the initial segments of Poisson's treatise. Section 1: Introductory Principles and Definitions. Poisson's initial section sets the stage by establishing fundamental definitions and principles governing heat. He begins by framing heat as arising from the vibratory motion of the constituent particles of bodies. This conceptualization, reflecting the caloric theory's waning influence, asserts heat's connection to kinetic energy, laying the groundwork for mathematical modeling. Poisson defines temperature as a measure of this internal movement and heat as an expression of its quantity. He invokes the principle asserting that the temperature of two contiguous bodies will equilibrate. He further introduces the concept of specific heat as the quantity of heat required to raise the temperature of a unit mass of a substance. A central claim here resides in Poisson's declaration that the propagation of heat conforms to mathematical laws, explicable through differential equations. He underscores his belief that the behavior of heat, even the most complex scenarios, is fundamentally governed by the principles of mechanics, thereby opening the door for mathematical derivation. Poisson's initial assertions of the equivalence between heat transfer and molecular motion, while forward-looking compared to the caloric theory, carry the implicit difficulty of translating the atomic nature of matter into cohesive macroscopic equations. This section's strength lies in its precise articulation of the work's fundamental assumptions, specifically defining heat's molecular nature and the applicability of mathematical methods. Any subsequent evaluation must consider these initial premises. Section 2: Differential Equations for Heat Conduction. Poisson's second section is central to his work. He derives the fundamental differential equation for heat conduction in solids. He builds upon the assumption of heat transfer by molecular interaction. This allows him to craft an equation that takes into account the substance's thermal conductivity, identified as a coefficient representing its capacity to transmit heat. He constructs equations for 1, 2, and 3 dimensions, using a detailed analysis of infinitesimal elements of a body. This section's core claim involves the assertion that heat movement obeys the law of diffusion. The process can be meticulously constructed through the application of the principles of differential calculus. Poisson arrives at the classic heat equation, though differing slightly in notation from that used today. He introduces the concept of a thermal conductivity coefficient. He also assumes the material properties are independent of temperature, a simplification which has a significant effect in the later sections. His method for deriving the heat equation, while mathematically rigorous for the era, relies on several approximations based on the assumption of a continuous media. The validity of these approximations is dependent on the physical scale of the system. Poisson's approach, while powerful, relies on the existence of thermal equilibrium. He assumes that heat disturbances equilibrate instantaneously. This could introduce problems in scenarios where the speed of the heat movement becomes essential. Section 3: Solutions for Special Cases: One-Dimensional Heat Flow. Section 3 delves into the solutions to the heat equation in one dimension, analyzing heat flow across a conducting rod. Here, Poisson specifically develops solutions for several boundary conditions, including constant temperature at the endpoints and a prescribed initial temperature distribution along the rod. The core argument of this section is that, for specific boundary conditions, the differential equations possess solutions that can be found through mathematical methods. Poisson uses Fourier series to solve the heat equation. He demonstrates the use of the solution, in this form, to model the heat profiles with elevated metallic. Poisson's use of Fourier series represents a significant application of advanced mathematical techniques to physical phenomena. He illustrates its use to represent complex temperature distributions as a combination of simpler, sinusoidal functions. This approach greatly expands the applicability of the heat equation. Poisson recognizes and discusses the implications of the boundary conditions on the solutions. He shows that the solutions are dependent on the temperature at the ends of the rod. The section's limitations perhaps reside in its reliance on idealized assumptions. The solutions presented are valid for a specific set of ideal conditions, namely those under laminar flow, which are not always reflective of real-world scenarios. Poisson successfully demonstrates, however, the predictive power of his mathematical model, providing solutions that align with laboratory observations. Section 4 Analysis of heat flow in 2 and 3 dimensions. This section expands the analysis to 2 and 3 dimensions, considering heat flow in plates and solid bodies. Poisson applies similar methods to derive equations and solve for temperature distributions across these more geometrically complex settings. His core claim is that the same fundamental principles and mathematical techniques can be extended to higher dimensional spaces. Poisson's solutions become significantly more complex to calculate than in one-dimensional. He utilizes techniques such as the method of separation of variables to discover partial solutions, further illustrating the versatility of the mathematical model. Poisson analyzes the impact of the shape of the body on the temperature distribution. He recognizes the crucial role of boundary conditions in determining the solutions. This section highlights the work's ability to model real-world scenarios beyond the idealized rod. Poisson's commitment to mathematical rigor, however, leads him to adopt simplifying assumptions necessary for deriving tractable solutions. Difficulties arise from the complexity of many physical situations that demand consideration of irregular geometries or non-uniform thermal properties. Nevertheless, Poisson presents a vital illustration of the adaptability of his mathematical framework, demonstrating its applicability to progressively sophisticated scenarii. Section 5. Applications to specific materials and phenomena. Here, Poisson begins to apply his theoretical framework to specific materials and phenomena. He discusses the behavior of heat within different materials, analyzing their thermal conductivities and specific heats. He uses experimental data where available and discusses how the theory accounts for these variations. The central claim is that the mathematical model can be successfully applied to predict and explain the observed behavior of various substances. Poisson specifically addresses the thermal behavior of metals such as iron and copper, as well as other materials such as wood and water. He uses experimental results to establish the thermal conductivity of these substances. Poisson's use of experimental data represents a significant intersection of theory and practical application. He implicitly acknowledges that the success of his framework depends on the ability to accurately represent the physical properties of substances. This section reveals the limitations of the model when faced with complex scenarios. The model's accuracy is limited by the quality of the experimental data, and any uncertainties in measurement will have a direct impact on the predictive power of the model. Poisson confronts the challenges of applying his mathematical model to the real world, but he successfully showcases its capacity to describe both the behavior of heat and material properties. Section 6 Discussion of steady state and transient heat flow. Poisson delves into a distinction between steady state and transient heat flow. Steady state flow describes situations where temperature distribution remains constant with time, while transient flow describes the dynamics as the system approaches equilibrium. Poisson analyzes the mathematical properties of each scenario, deriving equations that govern the temperature profiles. The core claim is that the mathematical model provides a coherent description of both the static and dynamic aspects of heat transfer. Poisson differentiates between situations where heat flow has achieved dynamic equilibrium and those where it has not. He applies his methods to derive equations for the temperature in both situations. This section is of particular significance because it elucidates the work's potential for studying dynamic phenomena, such as heating or cooling processes. The work's utility is apparent in describing the time-dependent development of thermal profiles, while Poisson's framework provides an effective description of a broad range of thermal behavior. The simplification of a uniform thermal conductivity presents an area for potential improvement. The assumption of instantaneous equilibrium may render less accurate results, especially when examining fast-moving dynamic processes. Regardless, the ability to distinguish and analyze steady-state and transient heat flow is a notable contribution to the understanding of thermal phenomena. Section 7 Consideration of radiant heat and its relationship to conductive and convective heat transfer. Here, Poisson discusses heat radiation, a phenomenon of key importance. This segment builds connections between radiation, conduction, and convection. Poisson attempts to integrate these aspects into his mathematical framework. His core claim is that while his theory focuses primarily on conduction, radiant heat should be regarded as a different, yet related, phenomenon. He uses this section to investigate these phenomena. Poisson identifies the challenges of modeling radiation. He acknowledges the need for further study. Compared to the in-depth treatment of conduction, Poisson's analysis of radiant heat is less detailed. He appears to have recognized the challenges of integrating radiation into a singular mathematical framework. This section represents a transition towards a more comprehensive theory, one that goes beyond conduction. Although the theory does not fully encompass radiant heat, it constitutes an early contribution to the unification of different heat transfer modes. The section's strength lies in its acknowledgement of the other modes of heat transfer. Section 8 Mathematical Theory for Heat and Applications to Engineering. In his final section, Poisson synthesizes his mathematical model, demonstrating its practical applications in engineering. He discusses the implications of his findings for practical applications. The central claim is that the mathematical model can be the helpful instrument for solving engineering problems concerning heat transfer. Poisson offers examples of how his theory can be applied to analyze the heat transfer in various industrial settings, such as furnaces and steam engines. He emphasizes the value of his mathematical framework for designing and optimizing such systems. Poisson directly addresses the potential impact of his work on the development of engineering and technology. He describes how to use his equations to predict the thermal behavior of various systems. This section offers a practical dimension to the work, underscoring the work's relevance beyond the realm of theoretical physics. Although limited by the assumptions inherent in this method, the capability to solve many thermal problems in engineering demonstrates the pragmatic utility of the theory. The closing segment successfully ties together the theoretical implications of the work with tangible application to specific industries. Conclusion: Siméon Denis Poisson's mathematical theory of heat, published in 1835, makes a substantial contribution to the understanding of thermal phenomena. This essay has systematically examined the key claims, methodologies, and arguments presented within the work. Poisson successfully establishes a mathematical framework for analyzing heat conduction in solids, deriving the fundamental heat equation and applying it to diverse scenarios. His detailed treatment of heat flow in 1, 2, and 3 dimensions, the analysis of steady-state and transient behavior, and the exploration of diverse materials each represents significant contributions. Poisson's strength resides in his rigorous application of mathematics to the study of a physical phenomenon, providing solutions for a wide range of boundary conditions and situations. The use of Fourier series in this work is a notable achievement, allowing him to solve the heat equation. However, the theory is dependent on several idealized assumptions, such as uniform thermal conductivity and the continuity of the medium. These are the areas where improvements would eventually be made. The work's enduring significance lies in its establishment of a mathematical foundation for the study of heat transfer. The concepts and equations developed in Poisson's mathematical theory of heat laid the groundwork for future studies on heat. The work is a seminal contribution to the evolution of physics. The work showcases the potential for combining theoretical physics with the practical applications. It has profoundly influenced subsequent generations of physicists and engineers and continues to inform our comprehension of thermal phenomena today.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.